In the second example of logarithmic differentiation, you can see that this function is a lot different than the previous video, which had x to the cosine x. It was weird but small. This is weird and gigantic. Okay, so I don't see any ln's anywhere in this problem. All I see is a hot mess. Like if I were to try and take the derivative of this just the normal way, I'd have quotient rule, with product rule, with chain rule, and with trig functions. So no thanks. If I could try a different approach, let's do it. So the different approach is, let's throw an ln into the mix. At first glance, this sounds like a horrible idea. But here is the benefit. The benefit is that I can use log properties to break this in pieces. So I have a quotient, which could be subtraction. I've got a product, which is addition, but because they're both in the denominator, that will be subtraction. And then I have this, which is a power that can come down. So as I kind of go through it in bits, what's going to happen is this will be the ln of 5x squared plus 1 to the 1/2. Okay, so that will be that first piece. Minus the ln of x cubed plus 1 minus the ln of the tangent. And again, the reason why it's subtract is because this would be addition, but because all of it is in the denominator, I would distribute that negative. Okay, now before I go take a derivative, there's one more thing I'm going to do. I'm going to take that 1/2 and write it down in front. Okay, now I grant you that this is a mess, but this is going to be a bunch of baby derivatives versus disgustingness up there. So I'm going to go for it. Okay, so this side's going to always basically look the same. It's going to be 1 over y dy dx. That's going to be the derivative of this side. So 1 over y dy dx. Okay, this piece, 1/2. All right, the ln of stuff is 1 over stuff times the derivative back upstairs. So the derivative of 5x squared plus 1 is 10x, but it has to go back upstairs. Okay, we have another one to practice, so let's try this guy. The derivative of x, the ln of x cubed plus 1 is 1 over x cubed plus 1 times the derivative of x cubed, which is 3x squared. Minus, okay, and then over here, I'm going to have the derivative of the ln of tangent is 1 over tangent times the derivative of tangent, which is that lovely secant squared. Okay, now I got to pause this for just a moment so I can get myself a little bit more room. Actually, give me one more second. Before I rewrite this, here's what I'm going to do. I'm going to squish these guys together. So when I squish, the 10 and the 2 will reduce to a 5. So this will be 5x over 5x squared plus 1. Okay. I'm going to squish these guys together, which is 3x squared over x cubed plus 1. And then I'm going to squish those together and not do anything creative. I'm going to be lazy and just call it a secant squared over tan. Do not care. That's cute enough. Okay, now I'm going to pause. All right, these problems take a lot of paper or a lot of board space, and I'm working with a very small board. So I had to rewrite where we left off. Okay, we are almost done with this problem though. Okay, so after you take the derivative of everything, I want to get dy dx alone. So I'm going to cross multiply both sides by the y. So that y is going to come over here. So I'm going to go y over 1, y over 1. Okay, now, dy dx is alone. However, we want it explicitly defined. That means all in x's. I can't have that y. So, thankfully, I still have y over here. I rewrote it. So that's what we're going to replace y with. So I'm going to go back over here, and where I see the y, I'm going to put that lovely answer. So what I have is dy dx equals 5x over 5x squared plus 1 minus 3x squared x cubed plus 1 minus secant squared x over tan x. And now I'm going to write in the y, which is the square root of 5x squared plus 1 over x cubed plus 1 times the tangent. And yes, it's gigantic and disgusting, but we survived. And you don't have to do any more algebra to this problem. We have derivatives of baby logs. I'm fine with all the little pieces, and we put the original guy back in. We're done. All right, so good luck on those examples or those problems in the homework. They're the last couple in that assignment. Keep at it. It's very repetitive. Practice is key.